So we're going to continue on with our electrophilic addition to alkenes. And now we're going to look at something called an acid catalyzed hydration. Now let's just kind of break down that word hydration. What do you think that means? Like if something is hydrated, what have you added to it? And if you're thinking water, exactly. Acid catalyzed hydration is the addition of water across a pi bond. Now I drew water like that because hydrogen will go to one carbon of the double bond and OH will go to the other. So those are our two groups that we're adding. Now here's kind of the catch, and please don't miss this. This reaction has to be acid catalyzed. If I try to take an alkene and add water to it, nothing happens. This hydrogen here is not electrophilic enough. So the way that we accomplish this is by doing this in acidic conditions. So maybe we do this in a solution of sulfuric acid. And I'm going to highlight this. I'll come back to it. It's typically dilute. I'll explain why in a little bit. But we throw in an acid. And if it's dilute, what else is there? Is it just sulfuric acid that's in that solution? No, there's water there. And there's a ton of it. And so in reality, this reaction occurs with hydronium. And the interesting thing is, we see the regiochemistry is exactly the same as hydrohalogenation. We're going to follow Markovnikov's rule. Hydrogen goes to the less substituted carbon. The OH goes to the more substituted carbon. Now, why do I highlight that hydronium is present? Because hydronium is what we're going to use in the mechanism. In the first step, we're going to use our pi electrons to pick up a hydrogen. Notice it's the same exact first step as hydrohalogenation. So we're going to do an acid-base or proton transfer here. And I want you to write this in your notes. Don't use water here. We will use water later in the mechanism, just not here in the first step. I'll explain why in just a little bit. But this is one of the most common mistakes students make in the mechanism, is they say, oh, hydration, I'm just going to add water here. No, we can't use water there, and I'll explain why in a little bit. Let's just finish this mechanism. So the hydrogen goes to the less substituted carbon to give us a more stable carbocation. And now we're going to use water here because there's plenty of it. Water's the nucleophile. So there's the hydrogen that we added, and now we have this oxonium ion. We don't like that. Oxygen doesn't like to have a positive charge. So we're going to do one last deprotonation step, use some more water. Where did the water come from? Well, we're doing this in aqueous conditions. There's a ton of water around. And we get the alcohol, I get an alcohol as the product. Now, let me go back to the beginning of this and explain why we don't use water. So this would be the reaction that we're trying to do. So why do I not use water in the mechanism there? This is bad for two reasons. Number one, water is not acidic enough to donate a proton to the pi bond. Or you could look at it as the pi electrons are not basic enough to pull hydrogen off of water. So that will never happen. That does not happen in reality, so you don't show it in the mechanism. Secondly, let's just say you could do it. The result of that would be OH. Well, if you're doing this in acidic conditions, OH can't exist in acidic conditions. Right? So if you were to draw this mechanism by starting off with water in this first step, you were going to get points taken off. If you show OH minus attacking this carbocation, you're going to get points taken off because OH minus cannot exist when you do these reactions in acidic conditions. Okay, so that's why the first step always uses hydronium. Now, one of the things you might be thinking about is, wait a second, didn't we just do something like this or something looks familiar compared to a previous chapter? We took an alcohol and concentrated sulfuric acid to do an E1 elimination. Wait a second. Look at this and look at this. What are they? They're just reverse processes of each other. So this reaction that I just highlighted, this acid catalyzed hydration, is in an equilibrium with elimination. So this is an elimination addition equilibrium. If I use concentrated sulfuric acid, it favors the elimination product. If I use dilute acid, it favors the addition. So concentrated acid favors the elimination. Dilute acid favors the addition. Now, why is that? Let me add one component here. One of the products of the elimination is water, right? That's where our leaving group was. So kind of think about this. Go back to GChem, think about equilibrium, how we can push equilibriums to various sides, reactant side or product side. In a dilute solution of acid, what do I have a lot of? This dilute solution is mostly water. If I have a lot of water, what direction does that force the equilibrium to go to alleviate that stress? That forces it to go back to the reactants. So that's why dilute solutions of acid will favor making the alcohol, doing the acid catalyzed hydration. Okay, so I've already highlighted the regiochemistry. Okay, I said we're going to follow Markovnikov's rule when it applies. Let's talk about stereochemistry. Do I need to worry about that? Absolutely. It's the same as the addition of HX. If you make a chiral center, forming a chiral center makes a racemic mixture. And then to kind of conclude, do I still need to worry about rearrangements, carbocation rearrangements? Well, what do you think? If the mechanism we're drawing involves carbocations, yeah, you always have to ask yourself, is a more stable carbocation possible? So yes, that always needs to be in the back of your mind.